Greetings, friends. My name is John Gabriel, and this is the New Calculus channel. So if you'll recall, in the previous Musings, I talked about real numbers and Cauchy sequences and all that. And in this video, I'm going to continue that conversation with more themes along the same lines. So let's begin. Okay, so really, one of the greatest disappointments of my life has been not being able to convince mainstream academics of these truths. And but let me just say that not all of them have rejected my claims. More and more are beginning to understand now and to accept these truths that I have been claiming all along. But to me, one of the big problems, excuse me, is that number is the most important concept in mathematics, and mainstream academics have no clue and do not understand what it means. So they talk about repeating decimals and non-repeating decimals and non-repeating, non-recurring, etc. But really, when we talk about decimals, we're talking about measure and converting numbers into the decimal system. I talked a lot about that in the previous video. Simon Stevin's Dedekind, if you recall, and how he devised an arithmetic that allowed one to learn certain rules and perform any arithmetic operation without actually understanding the theory of fractions at all. Okay, so let's begin. Let's answer these questions in this particular video. Does a third have a measuring decimal or base 10? Is this 0.333 followed by an ellipsis a unique representation of a third in base 10? And does multiplication distribute over an infinite series? And finally, does it make sense to define S equal to lim S, as is the case with Leonhard Euler? So let's answer these questions. Well, consider that any representation of a third in base 10 to any n places is never unique. Okay, so since infinity is not a taskable process or one that can be completed, 0.333 dot 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 cannot be a measure at infinity. Okay, so if you can't go to infinity, you don't have a unique representation. All right, and it doesn't matter that you know what the digit at any nth place is, because you can tell what the digit at any nth place is even with those numbers that have even with those magnitudes that have no measure, things like square root 2, pi, e, etc. You can also tell to any n places what the digit will be. Big deal. It doesn't matter if it's a trillion or more than that. Whatever you have, whatever you calculate, is never the measure of an incommensurable magnitude. All right, so if one could hypothetically assume that such a representation is unique, then it would contradict the theorem. By the way, you know why we call theorems theorems? Because they're true, right? So if you say 0.333 followed by an ellipsis is a representation, you're saying that 1/3 has a measure in base 10. Because that's what we do when we convert numbers into decimals. Do you get it? So the theorem says that a third cannot be represented because 3 is not one of the prime factors of 10. What are the prime factors of 10? 2 and? Any guesses? That's right, 5. Okay, there is a delusional retort that the theorem applies only to finite representations. That's absolute BS. However, an infinite representation is never possible. So you might claim that you can do infinite with arithmetic with infinite decimal expansions, but that's absolute hogwash. For example, you can't multiply or distribute multiplication over addition or subtraction. As you see in this video here, and the link is up here, this video here is called Proof that the distributive property of multiplication over addition does not apply to infinite series. So go and study it. It's very important that you understand this. So no, you cannot do arithmetic with so-called infinite decimal expansions. This, and this are not infinite decimal expansions. They're very finite, and you can count the number of digits in them. All right? So what you're doing there is a finite addition, and you're just lucky that it works in this case, that it will give you 0.999, simply because there are no carries in this particular representation. And so that 1/3 and 2/6 and many other equivalent fractions repeat when an attempted measure is made in base 10 is a property of radix systems. Okay, people? This here is a property of the fact, this 0.666 and 3, property of the fact that a third has no measure in base 10. But it can be measured in many other radix systems, and I'm about to give you an example. So we could write 1 is equal to 1/3 plus 2/3, or 1 is equal to 0.1 plus 0.2 in base 3, okay? In base 3. And that will give us 1. But this is nonsense, okay? Because there is no such thing as an infinite decimal expansion. So is it a unique representation? It can't be unique for two reasons. One, a third has no measure in base 10, and there is no such thing as an infinite representation or an infinite decimal expansion. If there were, then you'd be telling me that you succeeded in measuring the incommensurable magnitude pi. That's doing the impossible. Not even God can do that. Do you get it? Think about that. Stop and think about that. You can't measure those magnitudes. That's why the Greeks called them incommensurable magnitudes, okay? Right. So infinity is not a cool concept. It is a junk concept. And my new calculus defines the derivative and integral without the use of these bogus concepts. So again, does multiplication distribute over an infinite series? As we've already seen, the answer is no. And let's see how you would add pi to a third if you try to use your bogus decimal expansions. So here you have 3.14159 plus 0.333. But that is not equal to what you see on the right here, because a carry takes place when you try to add 9 to 3, okay? So do you see that your thought processes are entirely garbage? And how to put it, you're morons. And I mean that in a nice way, if it were at all possible. You're incorrigibly stupid. And when you peddle these things to your students, you're doing them a disservice. All right? So you might turn around and say, but 0.333 is just another way of writing 1/3. It's like saying that a half is equal to 2/4, 4/8, etc. You would be wrong in thinking this way. Why? Because a quarter and 2/4 are well-formed numbers that represent the same number, but the measure is different. A half is one part of two equal parts whose sum is the abstract unit. 2/4 is two parts of four equal parts whose sum is the abstract unit. And this is not a number. It is shorthand for this series, right? Euler later redefined this garbage as the limit of the series, which is 1/3. So why is this really stupid and absurd? Because you end up having three different rules if you adopt S is equal to lim S. The first rule says that the series, in this case, is the number a quarter, okay, and the series is the limit. The second one says the limit is not in the series, and it is the number a third, okay, so the series is not the limit. And the last one, it's indeterminate because pi is not a number, it is a symbol for an incommensurable magnitude. So this above example here, 1/5 plus 1/20 says that the series contains the limit a quarter. This one here says that the limit is not contained in the above series, but can be shown to be the rational number 1/3. And the final one, it's not in the series and it's not a rational number. For fuck's sakes, what is it? For those die-hard, driveling, sliveling, mainstream morons, it should again be said that this 3.14159 ... does not represent pi. We know the limit is not contained in the series, for if it were, then pi would be a rational number, but we can prove easily that pi is not a rational number. So mainstream idiots call pi a limit when it hasn't yet been established that the limit can be measured or described by any number. Okay, so in the next video, which I hope to be producing soon, I'm going to once again talk about the fact that there are no axioms in mathematics. And it's mind-blowing because I do it in a very detailed way, even more detailed than you might find in my free ebook. So subscribe to my channel, spread the news, and download my free ebook. And here's the link. And I hope that you're all staying safe in these very perilous times. Perhaps one of these days you won't hear from me again because COVID-19 might catch me. And that wouldn't be such a bad thing, I suppose. But anyway, this is the New Calculus channel, and my name is John Gabriel. Till next time, goodbye.